I have always felt, in the realm of astrophotography, that globular clusters are overlooked and underappreciated. But these fascinating fossils of the ancient cosmos are filled with mystery and things to teach us. As we talked about in the previous video on developing globular clusters, there is a strange mystery of their combined mass. You see, it's been observed that the combined mass of the globular clusters seems to match the mass of the superblack holes at the center of galaxies. And there is the fact of their amazing density. A single globular cluster can pack millions of stars into a small volume of space. Messier 5, otherwise known as the Rose Globular Cluster that we see before us now, is only 165 light-years across. Yet, it contains an estimated 100,000 to 500,000 stars. That is an average of 0.25 stars per cubic light-year throughout the entire globular cluster, and in the densely packed core, there are thousands of stars per cubic light-year. It's unbelievable. Imagine what the sky must look like from the heart of that globular cluster. In fact, let's do more than imagine. Let's take a look. Here, we are just a few hundred kilometers above a small, airless, ringed planet, 0.9 light-years from the globular cluster's central small black hole. The stars here are so thick that even the night side of this planet is bathed in a perpetual twilight. Let's descend to the surface. From the surface of this planet, as depicted in the virtual planetarium space engine, there is no place we can go that is dark. Vast thickets of stars illuminate the night side of this planet's sky like many full moons. It's hard to be exactly sure how many stars are in globular clusters, because the stars are packed so densely, so we can only see the stars that face toward us, and must estimate how many stars might be on the other side of their spherical shapes. Galactic clusters are also filled with very faint, low-mass stars that are difficult to observe against the globular cluster's combined brightness. And globular clusters are often thousands of light-years out from our galaxy, allowing a great deal of interstellar dust to come between us and accurate observations. In many ways, globular clusters can come across as relatively changeless. Spheres of dense stars, many galaxies believed to have few, if any, planets, and relatively static since the dawn of the cosmos. But in this matter, they can certainly deceive us. Globular clusters are realms of light, filled with color, and they're quite extraordinary. The Messier 5 globular cluster is filled with probably hundreds of thousands of stars, and most were birthed near the beginning of the cosmos, over 12 billion years old. The most massive of its earlier stars long ago ended their lives in spectacular supernovae, and the matter they put off has long since drifted away or found its way into other stars. Many of its stars have aged into cooler red giant stars, while some of its other stars have further evolved into blue horizontal branch stars. These are ancient helium-burning stars that have shed their hydrogen envelopes, leaving their hot, blue cores exposed. And also among Messier 5's many red-blue giants and red dwarf stars are blue stragglers, new stars created by the transfer of mass between one star and another, or even collisions between stars, which is not all that unusual in the densely packed space of a globular cluster. Recently, I decided to set myself a new challenge and see just how close to NASA or ESA quality that I could image globular clusters. This isn't one of those "can I image as good as the Hubble" self-challenges either. The mirror of the Hubble telescope is a couple meters across, which is to say it has a lot of aperture. In fact, the diameter of the Hubble telescope's mirror is 2.4 meters, and it has the advantage of imaging from space, where it does not have to contend with the problems of shooting through Earth's atmosphere, while I am imaging from the top of a low mountain just a couple hundred meters up, using a Schmidt-Cassegrain telescope with a mere 203 millimeters aperture. The only advantage I have is an extremely low bortle, but the Hubble telescope has no bortle at all. In other words, there are no atmospheric effects whatsoever for it to contend with. In that sense, this contest is no contest. It's more a challenge. How much color, how much detail, how much light, how much of those very faint, countless red dwarf stars within a globular cluster, specifically the Messier 5 globular cluster, can I pull out of the detail? And I think it's worth a challenge because Messier 5 is scientifically very interesting. It has over 100 variable stars, many of them of the RR Lyrae type, which serve the role of standard candles that astronomers use to measure intergalactic distances. Most of its stars are very old, low-mass red giants, though it contains a surprising number of rejuvenated stars, those blue stragglers that I mentioned earlier. Between them and the blue horizontal branch stars, the rose globular cluster offers striking color. It contains at least 7 millisecond pulsars, 5 of which are in binary systems. It even has a dwarf nova. Last winter was the cloudiest I have ever seen. There was not one single really good night during the entire winter. There was one clear but extremely windy night, and there was too much fresh, blowing snow to open up the observatory. Then there were 3 clear nights directly under the full moon. All in all, from November until the end of March, there were only 2 good, dark, clear nights. And even one of those nights, while clear, was still not great for astrophotography because the seeing was terrible. So, I was delighted in the second half of May to finally get 3 straight clear nights when the moon was still fairly dark. I used one night to finish collecting information on my previous globular cluster, Messier 13, the Great Globular Cluster in Hercules, and used the second 2 nights to begin gathering information on the Rose Globular Cluster. If you've looked at many images of globular clusters or tried to shoot them yourself, you will have experienced how they transform from faint outer regions to extremely bright inner regions, and that presents a challenge in developing because if you develop for those inner stars, you lose those faint outer stars. If you develop for the outer stars, you'll blow out the cores. On top of that, globular clusters appear to be haunted with these things I call light worms. They look like ghostly tubes of light that can appear anywhere in the globular cluster, but especially in the mid and core regions. Well, I figured out the way to resolve all these issues. It's a straightforward method of dealing with that extreme brightness range of globular clusters, as well as a way to bring out their beautiful color, which is often washed out in their own brightness. So, with that said, here's the NASA/ESA image, and here's my image. Please be kind and bear in mind that so far this image only has 6 hours of integration. While I did have 2 full nights on it, I'm far enough north that at present we are close enough to the solstice that the summer nights are already extremely short. In fact, I only get about 4.5 hours of astronomical darkness at this time. Because nautical twilight and nautical dawn last so long, I can shoot about 15 or 20 minutes into either side of that. The amount of light creeping into the sky at that time amounts to maybe the equivalent of an eighth moon, perhaps a quarter moon. But it's easily manageable. But in either case, it means I can only manage about 5 hours of integration per night right now. After calling out the less than ideal subs, I was left with about 3 hours of integration per night, giving me just a hair under 6 hours of integration to work with for this image, and I plan to double it. We're supposed to get about a week of rain, and then we'll be under the full moon for about a week. But after that, as soon as I get some clear nights, I can start shooting Messier 5 again, and my goal is to put about 12 hours of integration in total on this object. So, right now, this image I believe has brought out a lot of detail and roughly matches the NASA/ESA image for color and light quality, though not really yet for fine detail. It's fairly quick and easy to capture low-frequency information, color, and light and shadow, but fine detail takes lots of integration. There are still a lot of light worms in my image, and light worms means there's more information to resolve. Information that, in the case of globular clusters, will reveal faint stars or stars lost in that brightness. More imaging time will bring that out. However, this is a fairly bright target, and 6 more hours will get me where I want to be with it. Those extremely faint red dwarfs might require another 6 to 10 hours, but this target will not be well positioned long enough for me to have a chance to go for those. At least not this year, not unless I get really lucky with the weather. Now I know, even as I work on this project, there is no way for me to resolve as much extremely fine detail as the Hubble telescope can because it has a much bigger mirror and it simply doesn't have to deal with the atmosphere. So I'll never really be able to match this NASA/ESA quality. But I do intend to push the aperture of my telescope as far as I can and see just how much detail I can pull out, and try to get this image as close as possible to the incredible quality that you see in this amazing Hubble image. And if you've given any thought to shooting globular clusters yourself, but thought perhaps they were boring or they're too challenging to develop, give them another look. They are like spectacular fossils or microgalaxies, amazing deep sky objects, well worth our interest, beautiful, and well worth taking the time to image, I think. Shoot them entirely in broadband color or in RGB if you are using a monochrome camera. Ideally shoot them beneath dark skies and apply high dynamic range developing techniques, and you'll be able to pull out all the information within them. And if you're new to astrophotography and that's all Greek to you, just take a look at the video that I linked and it'll walk you through it. As always, thank you for watching, and if you keep an eye on this project, let me know how close you think it's getting to the quality of the NASA/ESA image. I'll also link the NASA-ESA image in the description so that you can take a look at it in its full, unadulterated, and beautiful resolution. Now, I'm sure you know what comes next. Get out there and shoot that amazing sky.